Our speaker this evening is an expert in graphs and large-scale analytics. Please welcome the CEO of Blazegraph, Bebee.
Thanks very much. I guess obviously you know the name of our product at this point. I want to talk to you today about sort of general graph applications, how you can use GPUs to accelerate graphs, and in general, I'd love it to be an interactive session. So if you have a question or you see something, just shout it out and we'll take it from there. So with that, we'll go ahead and get started. How many people are working with graphs in here currently? The graph database or graph analytics? Okay, great. How many people are working with GPUs or CUDA? A couple? I saw the people move Pascal pretty quickly. So graphs are not just nodes and links or edges and vertices. Graphs represent an important data structure. Anytime that you need to represent complex dependencies in your data, so you have time series or bipartite graphs of DNS lookup queries, graphs turn out to be a really important data structure. And so they're critically important for machine and deep learning applications. The challenge with graphs is that as they get very large, and what you see on the left here is a map of the internet sort of circa 2006, they become data structures that challenge existing computational models. And so getting good performance as your graphs get very large is very challenging. We sort of started off in the space with an open source platform. It was originally called Big Data, started in 2006. Big Data was inspired by Google's big table architecture. So it was a ground up graph database implementation using a B-tree model underneath. And as you can imagine, in 2014, having a product named Big Data, while it was quite cool to say, yes, we own bigdata.com, and we had the foresight, was just incredibly confusing. So just imagine trying to Google Big Data and coming up with an RDF for a graph database. It's not going to be your first hit. And so 2 years ago, we rebranded the platform as Blazegraph. And so it's the same core technology underneath, but now operating under the brand of Blazegraph. And then in December of this year, we launched Blazegraph GPU. Blazegraph GPU is the first GPU-accelerated graph database platform offering, and it works seamlessly with our open source platform. And so use the same kinds of APIs that you're able to use with your other graph applications, add a GPU, and you can experience the GPU acceleration for your queries. In terms of different kinds of applications and spaces that we see, this is sort of our areas where we see the most traction. Life sciences, material sciences, precision medicine, cancer research, and genomic applications are all an area that we're seeing a lot of interest and a lot of activity in right now. They're spaces where they have both quality graph data and large graph problems. We're up here today, meeting with some of our customers in the financial space. These range really the gamut from time series type applications to sort of knowledge-based graph applications. So a lot of mixture there. We mentioned in the question answering the Wikidata query service. So about 2 years ago or a year and a half ago, the Wikimedia Foundation selected Blazegraph to power the Wikidata query service. That's now in production today, and that's essentially sort of the Google Knowledge Graph that was donated back out to the Wikimedia Foundation. And so the Wikidata query service is making that information available as a graph, public Sparkle endpoint, essentially. And so if you haven't checked it out, you should. You can go ahead and yeah, question in the back.
Do you have some kind of characterization of the number of nodes and graph edges that we're talking about in some of these applications?
Yeah, so absolutely. And I have a few more slides now. So life sciences applications range from sort of mid-hundreds of millions up to tens of billions of edges, and sort of they're pushing the limit out into the 100 billion edge space. Wikidata, for example, today is really not a huge graph. It's sitting at maybe about 850, 900 million edges. And by edges, I mean a triple, so sort of edge, link, or sort of vertex, edge, vertex. And so the larger applications, an area that's been very hot in the last sort of 3 to 6 months has been cyber anomaly detection, both from a commercial perspective and from a defense perspective. And so those graphs can get very large. If you're thinking about looking at the boundary of a network in a larger organization over any sort of significant period of time. It doesn't take very long to get a 10 billion edge graph or more, so you need to look at other techniques that you can use. And then sort of, rounding it out, I talked a little bit about cyber applications, but certainly there's a large number of graph applications that make sense both in the national security and defense realms. So this is one of the sort of big areas that we see. Precision medicine is a very hot area right now. You may have seen the White House announcement on precision medicine about a month or two ago. Graph applications play a key role in precision medicine. One of the big areas that we see, and we have a customer called SciAps, which is based in Palo Alto, which is one of the leaders in sort of precision medicine applications. They're using graphs to do knowledge-based data integration. So they take clinical data, they take omics data, they take treatment data, they take genomics data that's coming from different trials. They use a graph model to integrate that, and then they provide a query language on top of that. In their case, they're using a domain-specific language that's translated into Sparkle, but intended to help practitioners in the precision medicine domain. Question?
Can you elaborate? I'm not familiar with that term, precision.
Oh, yeah. So precision medicine, absolutely. In fact, I have a video. I'll give it a try. So this is actually this is not as good as
5 minutes.
45 minutes? No, it's about 2 minutes. I'll show. There we go. Well, that may not be successful. So let me just, I'll go back and just so precision medicine is essentially using data-driven approaches to personalize treatment. And so it looks at how does a particular disease or condition manifest itself specifically in you, and then what is the best treatment for that given how something's manifested itself. And so cancer is a really strong example here. Some of the most promising research in cancer is essentially looking at how a particular instance of a cancer exists inside of you or the person who's infected with it, and the genomics that you have, doing analysis on that, and then matching up very specifically a very customized treatment. And so this kind of approach is really delivering very, very good results, sort of in the medical community, both in general as a treatment area and then specifically in the cancer research area. So,
But how graphs are in the field? Because I can understand document database, I can understand relational.
yeah, so graphs play a couple of different roles in this space. So one is your knowledge-based data integration problem, and that's a really classic graph application. And so you have different data sources. Each data source has a different schema. You go through and you use an ontology or some sort of representation of that schema to model what each source looks like, and then you build rules to basically map the data from one source to another. So you can say a patient from this hospital system has a first name and a last name, and a patient from this hospital system has it in a slightly different format. But for our application, we're really going, when we say patient name, this is specifically what we mean. So they're using it for data integration. In the genomics side, a lot of the matching algorithms turn out to be graph pattern matching operations. And so when you're looking for sequences in the genome, those can be graph pattern matching operations. And then the other cases are similar in terms of materials and life sciences, and that's where you're looking at things like protein path networks and really trying to find receptors in the networks. And so life science is a very rich area because lots of biological processes are well modeled as networks. So the thing that's very interesting here is today their customers are seeing 5 to 10 billion edge graph problems, and they're predicting that sort of by mid next year they're going to be in the 100 billion edge graph range, and that's 100 billion edges is really a little bit more than today's technology can comfortably handle and deliver good performance on. And so they really need to look at different models to kind of achieve that scale.
So is that the current barrier that hardware can't?
The graph size?
Yeah.
Yeah, so graphs are really, getting the question, graph operations are really sort of, are not processor bound, so they're bound by memory bandwidth. And so, if you think of a
Sorry,
graph.
would you repeat that? They're bound by?
Memory bandwidth. And so graphs really aren't like another big data challenge. So you can't just take a large graph and stick it into CPU RAM and expect to get good performance out of it. And the reason is many graph applications, so if you think of something like a PageRank, an iterative graph algorithm, it might touch every node in the graph many times during an execution cycle. So you're going to have to go through all of that data. And so the memory bandwidth turns out to be really the key factor for getting good performance out of large graphs.
How is it then horizontally scalable? Because you are using like hundreds of GPUs. Are you providing a huge bus between them?
Yeah, so let me defer that one. So there's a lot of really exciting things about that. And I have a couple slides. So let me get a little bit further and then go back to that. Because we were at, it's been a kind of a busy a couple of weeks, but we were at the New Technology Conference at the beginning of the month. The Pascal and NVLink were really focused, and they specifically addressed some of those questions. So in terms of other graph applications, knowledge graphs are a classic graph space, and so looking at the difference between just asking keyword search versus an actual answering the question. It's the difference between getting a bunch of pages and the actual answer. So examples here are the Wikimedia Query Service that we talked about. Lots of cultural heritage applications, and these are places where organizations are trying to manage large sets of artifacts with catalogs and publishing type operations. This is another example of a material science use case, not so much healthcare related, but materials related. So they're taking, the NIH publishes something called PubChem. It's a publicly available set of chemical compounds. The core of PubChem is about 10 billion edges. In this particular case, it's a large chemical company. They're combining the publicly available data with proprietary material science information that they have, and then building graph applications to help researchers to be able to find, as they build new materials and compounds, to be able to use graph query and graph pattern matching to enable them to do that. So if they're looking for particular compounds that have various properties, or they're trying to engineer a new material for thermal resilience or something like that, they're able to try to use this and leverage that to pull it together.
Can you just ask why you had Eureka and Oracle in that slide?
Yeah, in that particular use case, for this data scale, they were considering 3 different solutions. And so one solution was the Eureka appliance. One solution was Oracle's graph offering, mainly because they were an Oracle shop. And then the other solution that they ended up choosing was a Blazegraph GPU solution. And so that's kind of why those the Eureka appliance is pictured there.
What is K80?
K80 is one of the Tesla class GPUs, and so it is what they call a Gemini GPU. So it's a single GPU card that actually has 2 GPUs inside of it. And so it was originally released for lots of deep learning applications, and it's sort of one of the largest cards that was available until the Pascal was announced a couple weeks ago.
You employing the regular clusters and general purpose clusters, or this is some specifics?
So for just general purpose computer Hadoop Scaleout type clusters?
With graphs, I guess. I mean, you're trying to say that you are capable of processing billions of nodes and billions of vertices, right?
Right.
And edges. So you employing the regular clusters, or it's some very specific clusters which are not
so we
general availability.
Right. So we have a range of different solutions. So we try and match the problem to the right right solution. So we have an open source platform that runs without GPU acceleration. We have
On the what?
on just a EC2 instance, any kind of Linux, commodity Linux.
On
box.
one machine or on the cluster?
We have on a single machine. So our scale up architecture.
On a single machine.
Yes. So this.
So how you be able to scale to the billions of nodes on the single machine?
So this application here is a sort of a law enforcement application. It looks at communication events that have geotagging on them, and so the application is essentially to keep 90 days of events in the graph database. Then if there's something happens and you want to take a look at particular events, you draw a box around, a geographic box around that event, and you
So
play
you're
back
not
the
processing
time.
billions of nodes,
So-
but billions of edges.
So this graph is 40 billion edges today, and it's hosted in an i2 8x large EC2 instance.
So you have enough memory on one machine to host billions of nodes, or billions of
That's right. So
Ages
So
and-
today our non-GPU accelerated platform in our scale-up architecture can process about 50 billion edges on a single machine, and that's a pretty beefy machine. So think 264 gig of RAM plus, and multi-terabyte of fast SSD. But in this case, they're at 40 billion edges. They're getting most of the queries are sub-second in terms of query performance.
So these machines are not general availability kind of commodity hardware. It's a special hardware machine.
Well, that case is actually just something that anybody could go on. You could go on EC2 now and get a i2 8x large CentOS or Ubuntu image and deploy and achieve that data scale. So it's just, or if you had a commodity Linux machine. Maybe we can chat afterwards as well. I can give you some more details from that perspective.
But you don't parallelize to the number of machines. You're using one machine.
Let me go a little bit further, because I have both a scale up and a scale out piece of it. So I think I'll be able to cover that one. And this is just sort of the last kind of example of a graph application, and we'll really get more into specifics of the technology. But this is a cyber defense application. These are looking at net flows, and so net flows are connections coming across the boundary of the network. And then this is a case where what's been done is done a PageRank analytic over the net flow, and then that was used to identify potential exfiltration. So that's a case where something inside the network was communicating outside of the network and it shouldn't have been. And so it's an example of not just a graph query application, but also an iterative graph analytic application. And this screenshot here is not our software. That's something from a company called Graphistry, which is one of our partners in this. And this is something that's being done for a large consulting company. But when I was talking earlier, this is really kind of gets to the point about why graphs are hard to process and hard to scale. We talked about the memory bandwidth edges, and so no matter how fast your CPU cores are, if you're going to have to process a large graph, the CPU cores are going to end up waiting for that graph data to page in from main memory. And so if you look at the x-axis here, you can see the access latencies and clock cycles for various different types of cache and main memory that are shown here on the y-axis. And if you look right across the top, when you go from cache into main memory, you can see you're paying almost a 5x performance penalty. And so that's really why existing architectures don't scale cost effectively for graph applications. And so this is looking at a common metric for graph performance is something called a GType or a gigatep. So it represents the ability to traverse 1 billion edges in a second. And this is looking at various different kinds of hardware architectures and the published performance numbers. And so this on the far left is from work that was done by Carnegie Mellon for the NSA, called the NSA Big Data Experiment. They published a paper. They used a large Hadoop cumulo cluster to process a very, very large graph. they did achieve linear scaling, but the throughput was only about 250 million edges per second. And it really speaks to using the right architecture for graphs. And so any kind of disk-based approach is really not going to give you the best performance for large graphs. The Cray XMT2 is a popular supercomputing application. It's similar, of course, to Eureka. This is based on their Graph 500s, which is a common graph benchmark score, and sort of an estimate of their performance. And you can see they're sitting at about $180,000 per GType. In 2014, we demonstrated breadth first search traversal over a cluster of 64 NVIDIA K40s, which are another NVIDIA GPU. And our demonstrated performance put that price at about 16K per GType. And then the Pascal, which is the latest GPU that comes out, does two important things for graph applications. It increases the amount of RAM on the GPU, and it increases the memory bandwidth to almost 740 gigabytes a second on the GPU. And that's going to drop the price, we estimate, by a further factor of 4. And so if you have very large graph applications, GPUs are very, very competitive in terms of price performance comparison.
And does this cost include like licensing?
No, this is just surely looking at if you take the published performance numbers and divide it by the cost of the hardware. And then there's other things that are really trending for graph performance. And so you were asking earlier about interconnects and other things. And so the Power8 platform is a very, very promising platform for being the first system that ships with NVLink, which is NVIDIA's new high-speed interconnect that does bidirectional 40 gigs between the GPU and main memory. And then it's also going to be one of the first platforms to have the Pascal architecture. And so we're actually on one of these boxes. They were just delivered just after the GTC, and sort of been doing some early testing. But this sort of combination gives you the ability to not just use the GPU RAM, but with the Pascal architecture, they have what they call a unified memory access. So you no longer have to think about GPU RAM versus host RAM. You can think about it in a unified way. And with NVLink, you can get almost 40 gigs a second of throughput for it. So this is really very, very promising for additional kinds of graph processing. It also means that you don't have to fit all of your graph on GPU RAM. And so you could do work sharing techniques where you process some of the graph on the GPUs and some of it in host memory, and you're able to continue to process large graphs, get good performance, but also not have to have the same number of GPUs.
Does the Watson software use graph?
The Watson software does use some graph concepts. It sort of started off using a little more graph, sort of semantic web type concepts than it currently ended up being in its current incarnation. So there was a question earlier about the kinds of different deployment models that we have, and so this is really, we try to have a deployment model that fits applications from embedded graph database applications to a scale-up model, which is really where you sort of go to a single larger server. We support about up to 50 billion edges per node on a single scale-up server. We have a scale-out architecture. Scale-out architecture uses sharding techniques to be able to distribute the graph across multiple different servers. There's some performance trade-offs between scale-up and scale-out that you need to think about. And then we have both a single GPU and a multi-GPU acceleration. And so, really, what we find is most important is matching the right architecture to your graph problem. And so, we try to have a solution that meets all of those different needs. Every time that someone chooses a platform, they do some kind of evaluation. And in the graph world, there's lots of benchmarks and other things. It was very interesting in terms of when the Wikimedia Foundation selected us, because of the unique nature of the Wikimedia Foundation, they published a publicly available Google Sheet that had all of their criteria and choices along with comments and weights. And so we're obviously very happy that we were selected, but it's quite an interesting read to take a look at. I don't know if anyone's checked it out, but I would encourage you to do so if you're into looking at graph databases. Certainly we gained some insights, and others you may as well. This is sort of our core platform that we're building on, which is the core Blazegraph platform. It supports both the RDF and Sparkle, sort of the semantic web graph standards, and then we support the property graph standards, and so that's the Tinkerpop and APIs. We support Tinkerpop 2. We've just released at the beginning of this year a Tinkerpop 3 implementation, and so we're sort of a little bit unique in that we straddle both sides of that graph world. We also have a number of different extension points to be able to do things to build your application. So if you need custom indexes, database triggers, lots of different extensions that when you're building real-world applications become very, very important. And this is looking at our high availability architecture. So again, this is sort of the scale-up model. The high availability architecture gives you essentially perfect linear scaling across 3 nodes. It uses Zookeeper to elect a leader. All of the rights are managed by the leader, and then there's only synchronization at the commit point. So you effectively have very low-level replication between the 3 instances of your HA architecture. People use this sometimes for a load balancing construct, where they'll be inserting into one of the machines and querying off of the others, or they'll use it to distribute the queries, the query workload. And this architecture again is, works effectively up to about 50 billion edges per server. The scale-out architecture is for when you need to go larger than that. And the scale-out architecture partitions the graph across different sort of data servers or tablet servers, if you will. And then what we add really is the ability to do graph query processing in an efficient way. And so the scale-out architecture is really designed for trillion edge type graphs. It also has some advantages for parallel loading that you can't get necessarily with the scale-up architecture. There is a trade-off. We usually advise people, if they have a graph problem that fits onto a single machine, to typically stay in the scale-up architecture until they get larger than that data scale, because your initial performance will drop when you move from the scale-up architecture to the scale-out architecture. So if you have a server with 50 billion edges in the scale-up architecture, and you divide that into 4 on the scale-out, you're likely going to see some query performance drop initially. You'll make that up over time, but there's a certain trade-off in looking at that.
Question about parallel loading.
Yeah.
So you don't do query during the right, you have to load the whole thing up and then you query it?
We do support, so the scale-out architecture, the scale-up architecture is a fully, all the transactions are fully ACID. The scale-out architecture has eventual consistency. And so, but you can, the data is visible after there's a commit point on the data server for incremental query operations.
So I'm assuming that the loading is micro-batching or something, it's not individual transaction?
No, it's batching. It's batching. And then one of the challenges with, if for example, you're thinking about key value stores for graph operations, is it's very hard for key value stores to deliver good performance for queries. And the reason is a key value store essentially has 2 different operations. It's sort of, you can either fetch a key or you can scan for a key range. And so when you're implementing a graph query on a key value store, what happens is you end up having to send a lot of data back to the client. So you end up having the client having to do a lot of joining on the data. So what we do in our scale-out architecture is we allow the data servers to coordinate amongst themselves. And so if you're looking here at a sort of a very simple Sparkle query, as subjects are matched in this subject variable, the data servers coordinate internally before sending the results back to the client. So this allows us to get good query performance in our scale-out architecture relative to other models of graph database.
So, I'm sorry, you mentioned property graph before, graph that I take your pop. So are you storing the data as a triple store from an RDF perspective, and then somehow posting graph property database queries on top of that? How's the underlying format?
Yeah, so as I mentioned again, we started with sort of a native graph database implementation. We support something called RDR, or reification done right. And reification done right essentially allows you a way to conveniently express reification concepts. And so, to not go too much into the graph nerd world for those who aren't already ensconced, so there's a big trade-off between property graphs and the semantic web world. And one of the key things that is somewhat awkward and difficult to do in the semantic web space is sort of make what they call a statement about statements. And so suppose that you have one fact that Brad is speaking at the meetup, but you want to actually assign some metadata about that and say, that fact that Brad was speaking at the meetup occurred today on April 19th, 2016. Making that kind of statement in RDF is possible, but it's not very easy to do. And so we have an extension that allows us to do that, and we use that internally to implement the property graph model on top of it. So sort of on to GPU acceleration. And so we talked about Blazegraph GPU. It's the first GPU accelerated graph database. What our goal is with GPUs and graphs is to make GPUs accessible and easy to use for graphs without having for you to write any CUDA code or C++ or any device-specific optimization. So really focused on trying to put in the right high level of abstractions and marry that up with the GPU performance. So Blazegraph GPU is essentially sort of a classic GPU acceleration type application. So you have your graph database, you're doing Sparkle queries, you're managing your data in RDF, and you add a GPU, and you're able to get query acceleration for conjunctive queries as much as 200 to 300x over our core platform. And so this technology was originally developed with some DARPA funding that we co-developed with the University of Utah Ski Foundation, or Ski Institute. And so this technology is basically now in general release as of Q1 this year. In terms of looking how it performs, one of the most common and oldest graph benchmarks is something called the Lehigh University benchmark, or LUBM. It's a simulated universities. So the U1000 here means that we run the LUBM simulator with 1,000 universities. So it generates data where universities have students and students take courses and faculty teach courses. And so this particular query is a Sparkle query. I think everyone remembers what Sparkle stands for, right? This is a Sparkle query that essentially asks the question, show me all the students who take a course that's taught by their advisor. And so, and of the 14 queries in LUBM, number 9 is one of the most challenging sort of conjunctive ones. It touches a lot of the data. And so if we look at the performance of this on our core platform, over this 170 million edge graph, we get 173,000 results, and it takes about 54 seconds. When we run it on our GPU accelerated platform, we get the same number of results, and we're able to do it in a little bit under 200 milliseconds. And so the potential for acceleration is very great. And now, truth be told, not every query benefits as much as this. And so the queries that benefit the most it's going to think back to the memory bandwidth. They're the ones that are going to touch the most data and have the most joins. And so your sort of complicated conjunctive queries are the ones that are really going to get the most GPU acceleration. And so
this GitHub is with one CPU or multiple CPUs?
So this particular example is done on a single K40 GPU. And the data scale here is picked so that it fits, this graph fits completely in memory for a single GPU. So we do have, the current generally available release only supports graphs that will fit in a single GPU RAM space. At the end of this quarter, we'll be releasing an update that supports graphs across multiple GPUs.
So the data is preloaded into the memory and then it's sitting there.
Yeah, that's right. And so the data is loaded in GPU memory, and then we actually do the query planning on the Java side and execute it. In fact, I'm going to just show you a quick example of that. Hopefully it will, So this is basically the core Blazegraph platform. And so if you download Blazegraph, you follow the instructions, you can basically start it up. What you see here is sort of a management type interface where you can create different namespaces. Namespaces are like a table space in relational database terms. They have different properties, and they basically represent a graph. And essentially what you can do is you can load, I'm just going to take a set of data here. So this is an RDF file that I have on my file system, and so this is just nothing special in terms of formatting the data for the GPU. This is just an RDF XML graph serialization. I'm going to load it, so I just used a common representation web interface. I've loaded it onto my graph. I'm going to go back. And choose to publish it to the GPU. And now my data is loaded on the GPU, and I'm ready to issue SPARQL queries that will be accelerated. And so I can go over, make sure I'm using this one. Select query number 9. And execute the query. And so this is on my MacBook, so the GPU has like a gig or 2 of RAM, so it's not, you don't see the same performance gains as you do on larger ones. But that's how easy it is to take advantage of using GPUs to accelerate your SPARQL query. There's no CUDA required. You can do it completely using existing graph standards, existing applications. Yeah.
Is that acceleration from just the fact that all the memory is there and accessible much more quickly, or because you're running it across many more cores?
It's mostly a memory bandwidth piece. In fact, one of the challenges in building Blazegraph GPU is there's really often not enough query work to really keep the GPUs really well utilized. And so, but it's really mostly the memory bandwidth piece.
For real-time time series applications, do you have some sort of chunking mechanism that is running from memory to the GPU memory on a sequential basis and processing it? And, obviously, you're limited by the amount of memory on the page or however it's arranged.
So today we don't. So today we support generally a sort of a publish, analyze kind of models. We see the need. We understand the use case for sort of a streaming update type model or a windowing model where you're keeping certain time windows up to date on the GPUs, and we have in our product roadmap that's scheduled in for Q3 this year.
How long does it take to load such a graph on the GPU?
Well, you saw that was a very small graph. It didn't take particularly long. This graph takes maybe 10 or 15 seconds to load in, but certainly in terms of thinking about graph applications, looking at the total time from data to analytic execution to analytic result to doing something with it is really an important part of what really putting it into operations. And so we looked comparing GPU accelerated breadth-first search traversals to Apache Spark, and this was Apache using for the GraphX libraries. And so this is looking at 3 different hardware configurations. The green here is looking at sort of a single fat node. And so this was a single node with about 128 gigs of RAM, 2 K80s, so it had 48 gigs of GPU RAM. And on that, only of 700 million edges of a 2 billion edge Twitter graph. And this was the ICWSM 2010 Twitter graph. We're able to fit into that GPU memory. But in terms of looking at the performance difference, we were saying 1400x. And this is making sure that we used in-memory RDDs in Spark to make sure that we were sort of factoring out the disk access piece. You can see going to a 16-node EC2 configuration with 16 K40, so you have about 500 gigs of CPU RAM on the Spark system versus 192 gigs on the GPU. We had 1800x speed up. And then on the red line, where you see 700x, there was almost 2 terabytes of RAM available to that 16-node cluster versus the 16 K40s. And we still got a 700x speed up. Now, obviously Spark, we love comparing against Spark, because Spark has lots of different ways that it uses JVM and creates a lot of heat pressure. But what it is indicative of is the amount of performance gain that's possible with GPUs.
But this mostly for graph traversal. So if you add any kind of computations to the queries, that will also touch like big space, big memory spaces, but they'll do simplistic computations on them. How does it change the performance?
Not significantly. So let me hold that one for about 2 slides and we can get back to it, because we have something that sort of addresses that. This is what we really see the challenge of GPUs for graphs as being, and this is you could generalize this and say this is the challenge of GPUs for data analytics, is the people who understand how to write good analytics and good algorithms aren't the same people who can make the code run very, very fast on the GPUs. And so I mentioned it from the graph database side, but our really goal is to enable people to write simpler and smarter algorithms and take advantage of the speed of GPU acceleration. And so the second GPU-related product that we launched is something called Blazegraph Dazzle. And the goal of Dazzle is to be as easy to use as Spark. So quickly get your data up and running, do some ETL on it, get going quickly, but as fast as you can get with the native GPU implementation. Dazzle itself is a really horribly long, difficult to pronounce acronym. What Dazzle is a domain-specific language for graphs that's written in Scala. And so it exposes sort of linear algebra operations as well as ways to parallelize the graphs in Scala, which can then be compiled down into CUDA kernels. And we also support user-defined functions. So your question in the back, so using Dazzle, you can write a graph traversal algorithm where one of the operations is some custom function that's written in Scala that evaluates the value of some piece at a point in time. And then we'll actually do the code generation and compile that down into CUDA kernels, and then we execute that on single or multiple GPU systems. And so it really enables you to stay at this much higher level and access the power and the speed of the GPU performance.
My question was how does introducing those custom functions changes the performance characteristics of the query? Because the GPUs, they have good bandwidth, but the processing speed that the kernels have, it's negligible. So any kind of serious computation that you need specifically for analytics, where you even need to run some, I don't know, some averaging functions, what you've seen is they start to degrade really, really fast.
Yeah, I can't comment on that specifically. We haven't seen a case where the actual function used in the graph traversal is causing a slowdown in terms of the analytic relative to what you can do on a CPU-based platform. And I think that, I suspect that for large graphs, that's going to hold true because you're really more performance bound on the memory bandwidth. We do see models where people are doing things like more traditional machine learning applications outside of the graph platform then they use the machine learning output to add new attributes into the graph, do some graph analytics, and then sort of do this kind of loop over again. So that's definitely a use case that we see. But I haven't yet seen cases where it's caused significant slowdown. And then, as I mentioned earlier, it's really great to be fast, but if it takes you 2 days to move all your data to the GPUs, it doesn't really matter if you can execute it in 200 milliseconds. And so part of the goal of Dazzle was to really make it easy for people to be able to move data to and from the GPUs. So we started out looking at kind of the Spark RDD mechanism and integrating with that. We've done that, and now we're also moving a little more broadly towards the data frames concept in general. And so being able to take the data frames, whether you have them in Pandas or in Spark, and be able to provide you the utilities to move them and publish them onto the GPUs, execute Dazzle analytics, and then get the results back.
So data you bring in RDF format always? Is it always ingested as RDF?
So there's two. So in terms of the Blazegraph GPU platform, the first one we looked at, yes. In terms of the Dazzle platform, Dazzle's really operating looking at the graph as a sparse matrix, and so
as far as the semantic meaning of the different columns or elements or whatever or nodes, is there an ontology that interfaces with that? And I'm just trying to figure out how you get from data point meaning to the functional or the domain specific point.
yeah. So I mean, there's definitely both Blazegraph GPU and Dazzle share a common runtime underneath. And so, with Blazegraph GPU, we've essentially taken sort of the Sparkle 1.0 spec and implemented it in concepts of linear algebra operators, as well as a couple of other similar get matches type arrangements. And so we take the RDF graph that you put into Blazegraph GPU, and when we publish it on the GPUs, we publish it essentially in a sparse matrix representation.
So you don't need an owl ontology.
You do not. And so all of the inferencing things are done sort of outside of the GPU space. We do have some ideas about that, but there's nothing that's in the project yet. And so this is an example of a Dazzle algorithm. So this is essentially a single source shortest path implementation. Essentially what we do here is we initialize the matrix, and then we just do a very, very simple loop where we're doing sort of a vector matrix product on sort of a semi-ring that we support in Dazzle, and that's it. That's the SSSP implementation. And if you look at it in terms of equivalent lines of our native CUDA SSSP implementation, it's much shorter. The other thing is it's much, much easier to tune. And so we were doing I showed earlier the page rank over the NetFlow data. We actually ended up doing 5 different implementations of the page rank algorithm before we found the one that worked best on that particular data set. And to do that and run it on the GPUs took, half hour or an hour to make the kind of changes and tweaks. Much, much less overhead than actually writing it in CUDA. And certainly, you wouldn't be able to kind of get up and running and do that kind of iteration in that time frame. And so we're very, very excited about being able to allow people to operate at this level of abstraction and still get performance from the GPU side. So,
can you explain what's happening here?
Yeah, I can. So this is basically this is all initialization, and so we're taking the size parameter, initializing the semi-ring, looking at the sort of default value, and then this is the data. So we're taking sort of the starting point. So this is in an SSSP algorithm, you're given sort of where am I going to start from, and then that's all the initialization. This is actually kind of just the run call. The worker class.
And what does this run call do?
The run call actually executes.
I don't see anything.
So I can go through this a little bit more afterwards, but basically this is just defining the function that's then called in the program to actually run the SSSP algorithm. So there's some Scalable program around this and you say run SSSP with this source vertice, and it calls this, and what we do underneath is we translate that into CUDA and execute it on the GPU.
But where is this function? You don't have this function. This function is not
It's on the right side.
It's on the right side.
Yeah.
It's an abstract
So
function.
you're saying that this is what's happening, and here is just abstract function that we don't know actually what's happening.
Let me go through this afterwards, if you don't mind.
Okay, we can go afterwards. But, this is kind of confusing thing.
Because on left it's API and right it's implementation. That's how I understand it.
Okay, so and what is this implementation does? It's just a couple of assignments. I mean, is that how you traverse the graph?
That's right. Yeah, so you basically, you're just iterating over the matrix, and you're updating the weights until you're done. And that's it. That's how simple the algorithm is.
This is three kind of this is for trees.
I'm sorry, could you repeat the question?
There are three graphs. Graphs which are named trees.
Oh yes, yes.
This is for trees.
No, not just trigraphs. I'm not sure that. Okay, but I'm happy to spend some time afterwards. So these are examples of the types of algorithms that you can implement in Dazzle. And so if you start from the left, you'll see things that are traditional graph type applications, so community detection, triangle counting. And if you move towards the right, you'll see things that are more on the machine learning side. And so this is kind of speaks to one of the questions that we had earlier, which is, how do you combine these things? And what we really see is a real blending of graph applications and machine learning applications. And so we think this is a pretty interesting and exciting space where people are both looking at graphs, applying machine learning techniques, updating the graph, and then iterating over it.
Question. So does this support like a Bayesian network, or will it be able to support a Bayesian network? Because that's the kind of machine learning you naturally want to do.
Yeah, so we're not on the recurrent deep neural network side or sort of that aspect of it. We're really focused very much on the graph traversal analytics and then sort of related clustering type activities that also are using the same kinds of linear algebra concepts. All right. And so I have a few more case studies, but I think I'm probably getting pretty close to the end of my time. And so I wanted to just wrap up, and then I think there's a question and answer session afterwards. And so just a kind of a quick pass for us if you are interested. You can vote for us on the Reader's Choice applications, and obviously I'd love to hear from you, and hopefully if you can stay afterwards and talk, that'd be great, and if not, we can follow up another way, so thank you.
Before we go on to Q&A, we're going to do a great round of applause to Bebee. Let's take the first question. You're going to want it really quick.
You mentioned using graphs for data integration. Can you provide a reference to find out more?
Yeah, so feel free to contact me. You can, the SciApps use case is the precision medicine case where they're using data integration. There's another one, the cultural heritage applications are a very big data integration case. And so research space in the British Museum, I have some slides I can send you, but they're essentially, the British Museum has the problem, and other Smithsonian does as well. They have too many artifacts, not enough physical real estate, and a mission to make these things available to the public. And so they have things from all different data sources and walks of wherever. They're using graph-based approaches to be able to organize those and provide ways to coherently navigate them, integrate virtual reality type constructs where you'll do 3D imaging around a particular thing allow people a VR experience. So that's another example of a graph data integration type use case for graphs.
Yes.
So GPUs emerged essentially as tools to be able to do high-performance graphics, and then were adopted generally across a variety of disciplines. The precedent for this in other applications, for instance, FPGAs have also been applied in some data applications. What's your thinking in the sorts of markets that you're talking to in terms of interest in specialized hardware, active memory, FPGA-based solutions, parallel associative schemes, optically coupled schemes for lookups, that sort of thing? In situations where where the derivative of performance of the GPUs is in essence less than the rate at which your data sizes are growing, which we think is going to be the case, let's say, over the next 10 years.
Right. So we've seen across all the spaces we're in, we've kind of touched against all of those things. So FPGA, there's a lot of stuff going on now about processor in memory, those kinds of technologies. Different markets have different levels of familiarity with it. So for example, we find like defense and finance tends to be more familiar with specialized hardware type applications where they have very low latency type requirements. Life sciences, precision medicine, unless they're coming out of an HPC background, there's less familiarity of that. And so it's a mix. What we see our space in is really in giving people high level ways to access the speed of the hardware. And from a future looking perspective, we're very, very interested in seeing more high speed interconnect support between the accelerators, be them NVIDIA GPUs or Xeon Phis, and the host memory, because we think that's kind of a much more scalable model for being able to handle some of these very large problems without having you to have 2,500 GPUs sitting around.
I suppose it's sort of amenable to offline conversation, but there's a point at which it seems that we've been talking about this for 30 years, the notion of having processors and memory combined, because at some point, traversals from media are essentially the point at which you'd like to be able to analyze it at all possible. You want to stream once in an ideal world.
Yeah, we should talk about it offline. There's a couple of interesting things going on in that space.
Yes.
The Scaleout Architecture sharding is it round robin, or is there some intelligence to that? And if so, what happens if you start adding those to the cluster?
So we do basically do a hash-based partitioning on the key. And so if you add nodes, we will basically just change the partitioning. We have a metadata service that's very lightweight that sort of allows you to associate a given value with which shard is
So if I add a node, I would have to reload the whole graph?
No, that's not correct. If you add a node, when you added new data, it would begin to populate that.
Just go to that one.
That's correct.
Time for just a couple more questions. Yes.
I've heard a lot about performance. What's the power consumption?
Good question. I don't have a good answer for it. I know that in general, if you look at the supercomputer programs or Coral or any of the top supercomputers these days are generally trending towards GPUs, and they have very good performance in terms of watts per flop. In terms of these numbers, I couldn't tell you specifically. I would guess that we're using them a lot less than the 16 Amazon EC2 C34X largest, but that's just a guess.
Am I able to try this today? Do you have a trial, or is it open source?
Yeah, so we have an open source version that you can download today. It works basically out of the box. You can the GPU technology is not open source, so you can contact us if you need to do evaluation.
That's all the time we have for questions now, but Brad will be here for one-on-one questions. Feel free to come up right now and ask him. Thank you all for coming. Thank you, Brad Bebee.